Hi, this is Buster with Buster's Motorsports. This is our second video. First video we were looking at 800 horsepower, 3,000 RPMs from a typical 5.9 Cummins, and I left out a few things from the video that I'm going to address this time. One of them is I gave some numbers that we needed for the turbo to perform to. Was, I don't know, 80 some pounds a minute at I think it was 4.6 pressure ratio, and I just went right to the compressor maps with those numbers, and I never told how I came up with those numbers. So here's just a quick little thing, and I use these on my phone, but since I'm videoing with my phone, I'm gonna do it on a laptop. One of the sites I use is called where are we at? Boosttown.com, and you go to the forced induction section and then go down to engine air amount calculator. I like that one. So basically you take your engine RPM, which we're using 3,000, your engine size, which in this case I guess they use cc's because you got to do 5,900 cc's for a 5.9. Volumetric efficiency, I always use 80. That might be a little conservative, and I'll put the boost pressure at 0 because a lot of times when I start out, I want to know how much does the engine consume with 0 boost, and that would be 17 pounds a minute, which is about 250 CFM. So basically a 5.9 running at 3 grand is going to consume that amount of air. Now, this website calculator will also allow you to put in different pressure ratios. I mean, you could put in 3 to 1. Let's see. And as soon as you hit the number in, it automatically, you have to hit calculate. So if you're running 3 to 1, which is basically 30 pounds on the gauge, you would be drawing in basically 69 pounds of air a minute. So anyway, that's one, and it's just pretty basic. The other one that I really like is Garrett's Boost Advisor, and this thing has come and gone a couple times. I had it on my phone, and then at some point it went away. Boosttown, basically, you give what your engine is and how fast you're spinning it, and it tells you how much air it's bringing in. Boost Advisor goes the opposite. Boost Advisor asks you, let me go back here to the beginning. So Boost Advisor says, how much power do you want to make? And for this video, we discussed 800. How many liters? 5.9. One turbocharger, diesel fuel, air-to-air, intercooler. We'll use 2 valves per cylinder for a 12 valve. Mid-range, let's just throw 2,000 in there. We want it to spool by 2,000. And we've decided that 3,000 is peak power. And I use 0 because I live on the East Coast. And that's something we're going to go back to a little later. Some of you guys out west, where you have high temperatures and high altitudes, it changes everything. I always use 70 unless I know that we're sizing something for the dead of summer. Show recommendations, and it never has any recommendation. In the old days, it used to bring up some turbos that Garrett thought would meet this criteria. Obviously, 800 horsepower at 3,000 RPMs is a tall order for any single turbocharger. In fact, it's almost impossible without putting a turbo way off the map. And Garrett's not going to suggest a turbo that's going to be basically run at the edge of its destruction. So anyway, so Garrett says you need, now if you remember before from our engine air mount, it said that we only needed, let's see, a 3-to-1 ratio. Actually, that's too low. We need 4-to-1. No, let's go back 3.6-to-1, which gives us 4.6 on the map. That puts us at 80 pounds an hour, which has kind of been talked about as being a amount of air in pounds per minute for 800 horsepower. So it's basically you times it times 10. Anyway, so this calculator says 80 pounds is going to give you, or it says 3.6 at 80 pounds is going to give you your 800 horsepower. Garrett, 86 pounds at, why is this saying a 987 pressure ratio? Something's weird here. What did I do wrong here? Oh, look, I put 14,000 pounds of boost. That's the problem. Huh. You know what? I'm going to go back through this. I might edit this part out because it's just a waste of time. I'm not really sure. I've never had that goofy of a number unless I put something really wrong in there. So we'll go to 800. Next. 5.9 liters. Next. I'm trying to keep these videos reasonably short, but I'll get better at them as I go along. But it's most important is to get the information in here, because those of you that want the information are going to be willing to watch a long, boring video. So do the best I can. Let's see. 3,000. Let's see if we come up with some more realistic numbers. Go back to 0 degrees, or 0 feet. 70 degrees. Show recommendations. Let's see. Yeah, that's a little more. That makes a little more sense. Okay. So 798 horsepower is going to require 71.5 pounds of boost, which is a 5.93 pressure ratio, 86 pounds a minute of air. So, so this chart tells me that in order to get to 86 pounds a minute, I need to be at 71 pounds of boost, whereas the engine air amount calculator is telling me that, let's see, let me raise that up a little bit to get it to go to, let's go 3.8, 4. No, let's go all the way to 4-to-1 ratio. There you go. So 4-to-1 pressure ratio, no, 4-to-1 boost, 5-to-1 pressure ratio is 87. Let's go back and compare that to Garrett. 86.5 at 71. I'm not computing my pressure ratios on the fly, but anyway, they're fairly close. I think Garrett takes in a lot more factors in its calculations, and I like that you start with horsepower and go with your engine size, and then it tells you how much boost pressure and how much airflow you need. Okay, here we go. It says you need a 5.93 pressure ratio, and this thing here said, see, this says you only need 5. More than likely, this Boost Town calculator is using all perfect stuff. It's probably using 59 degrees. It's probably using 2.992 altimeter reading, which is all a standard day, whereas Garrett is taking my 70 degrees. It's taking some other things, my intercooler, into account. So this is my favorite here. This is more of a down and dirty. If I real quick want to know how much air the engine consumes with no boost, I like to use this. Sometimes I want to know what it consumes without boost so that I can do all my own stuff. And then sometimes I just like to have it spit right out to me how much airflow and pressure I need. Anyway, so that brings me to the next thing that I didn't talk at all about last time, and that was density ratio. So we've been using pressure ratio, and pressure ratio is basically the turbo is taking X amount of pounds of air, and it's compressing it X amount of times, and that gives you a ratio. When your boost gauge is at 0, it's not really 0. Air weighs about 14 to 15 pounds out here in the atmosphere. And it depends on your altitude, it depends on your temperature as to what your barometer reading is. So at 29902 barometer, which is standard day, at 59 degrees at 0 degrees altitude, air weighs 14.7 pounds. As that goes up or down, the weight of air changes, but the turbo is a ratio producer. It takes whatever you're putting into it, be it 14.3 to 15 pounds, and it multiplies it. So boost gauge at 0 equals still 14 or 15 pounds. It may not make sense, but it's just the way it is, and that's how the compressor maps are all absolute pressures, whereas your gauge is an indicated pressure. So I hope I haven't made it more complicated, but anyway, so when you compress air, you introduce heat. You cannot compress air without causing heat. It's all part of the laws of thermodynamics, and laws are laws. There are no exceptions. So if you take air that's at 14.7 or 15 pounds and you compress it to 30 pounds on your gauge, that's a 3-to-1 pressure ratio, and the laws of thermodynamics say that when you compress air by that much, you're going to heat it. And guess what? The hotter air gets, the less dense it gets. Air molecules are moving, and at 59 degrees, they're moving a certain distance, and then at 350 degrees, they're moving a larger distance. The more the molecules move, the more space is in between them, thus the air becomes less dense. So let me go to this density ratio chart, and this is one of the things that we completely blew off in the last video. So let's say I got my 475 and it's putting out 30 pounds of boost, which is about 3.04 pressure ratio. I go up here to my compressor efficiency line. I don't know, I say a 475 will probably do, sorry about the, trying to get that to stop doing that. But anyway, 74% efficiency is a pretty good average. Run that 74 over, and guess what? What you thought was 3-to-1 is actually only 2-to-1. And I didn't talk at all about that because typically everything we run is intercooled, and the more intercooling you do, the closer you can get your compressor discharge temperature back to your ambient temperature, the better this efficiency is going to be. In all honesty, an ice water intercooler, which will take 350 degree compressor discharge air back down to ambient temperature, gets you to 100%. At that point, your pressure ratio is the same as your density ratio. So not very many people are running an ice water intercooler on the street, so you do have to take this into consideration. The other thing is in a set of compounds, and this is where this really becomes important. Say you got an S480, and your first stage you're going somewhere around 15, let's say 20 pounds. Let's say you're really rocking this baby. So 20 pounds on an S480, you're not going to have any kind of intercooling between your first and second stage. So 20 pounds, which is 2.3 pressure ratio, over to the left here, what started out as 2.3 is basically, it's like 1.55. That's not much. So that's why, and I've had some argument on this, that's why that especially in hot air and high altitudes, you need a way bigger first stage compressor than what you might think, because you're losing a lot through your density ratio. So there is another chart that has density ratio of an intercooled engine, and basically these lines take a little different. They curve up this way. And like I said before, if you could bring that back to the same temperature with ice water, this chart becomes unnecessary. And I don't often use the chart because everything we run's intercooled, and even an air-to-air intercooler on a 70-degree day is going to take 350-degree compressor air and bring it back down to, probably 130, 140 degrees, and that's pretty good. So the other thing that I didn't cover in my first video is other turbos. And so we were talking about, let me go back to since I like Garrett, we'll go back to Garrett. So Garrett says we need, for an 800 horsepower 5.9 engine at 3,000 RPMs, we need 86 pounds a minute. Now, I know that sounds like overkill, and the problem is the 3,000 RPMs. 800 horsepower at 3,000 RPMs is a very tall order. 800 horsepower at 4,000 RPMs is a lot more achievable. So we talked about so we talked about the 75 millimeter compressor, and this is the 400 SX, so this is not the fancy 10 blade billet. This is just your basic. Let's go down here to we needed 86 pounds a minute at, what was our pressure ratio? Almost a 6-to-1 pressure ratio. So, go back over here. One of these days I'm going to get a pointer, but I don't have one right now, so we're going to use this ink pen. So, 86 pounds. First of all, 6-pound pressure ratio is off the chart. You're up here. Actually, you're up here a good bit further. You're overspeeding the crap out of the turbo. So anyway, so we talked about this last time. We talked about how a 475 would barely get it done. The 480 would do a little better. 75 pounds. I need a laser pointer or something. 75 pounds up to, actually it's not going to work on an 80, because you could take it off the chart RPM wise and it'll still work. It just becomes very much less efficient. Like those lines in that pressure ratio to density ratio, the lower the efficiency, like down here you're at 74%. That's what we were using. Well, in reality, if you want to push a 480 to 6-to-1 pressure ratio, it's horrible. I mean, you're going to be up here into probably the 50%. So, the further you push the turbo off the map, the less efficient it becomes, which means you need even more pressure, and you're way beyond the limit of the speed of the compressor. So you're in danger territory. Reality is we often operate in danger territory. It's just what we do in the performance. So another thing I left out is I didn't talk anything about any of the other brands. So I'm going to grab another book here. And first off, let me just say, this Turbo Real World High Performance by J.K. Miller. This is probably the best. If you're going to buy one book to help you with turbo such stuff, this is the best book out there right now, in my opinion. This book, well, I have like several of them, but this is a really good one. So anyway, so let's go. Let's see how this works out on a whole set. And this book, when Jay Miller wrote this book, somehow he got whole set to give up. How can I do this? Oh man, I can't hold this and point at the same time. They got whole set to give up some compressor maps, and most of you know, whole set compressor maps are rare as hen's teeth. If you have any real ones, that's a pretty cool thing. Hang on to them. Let's go to HX60, because 800 horsepower is a lot. So I tell you what, I'm not going to point. I'm just going to kind of put the phone close So we've determined we need 87 pounds. So that's 2, 4, 6. It's right in this area. It's basically this line right here. So let's take that line up, the 80 whatever pound line up, and we're looking for 6-to-1 pressure ratio. Wow. All right, so once we cross over 4.5-to-1 pressure ratio, we're at 98,000 RPMs. Going up to 5, well, we're over 100,000. All right, so once we're up to 6-to-1, where we need to be, the HX60 is it's way oversped. It's oversped, and also, all right, I got to use my pointer here. Depending on where this line goes, once it passes 98,000, you're also getting close to the surge. And overspeed is still going to go till the turbo blows, but if you're operating within the surge line, you're done. It's just, it ain't going to work. HX55. This is pretty interesting. So HX55 at 87 pounds. It ain't gonna do it. It's way off. Here we go. This is an example of a turbo that flows the numbers. All right, so there's 80, 86, 87 pounds a minute right about here. This is an HX82. Look at that. Yeah, it'll do 5-to-1, but look how far into the surge you are. It is not gonna work with this. So, yeah, it'll do it. Won't even be a terrible overspeed, but you're gonna be surging to where it's gonna be ineffective. Here's some more whole set ones. So let's go over here. We're in the 80 pound a minute at 6-to-1 ratio. The one closest to doing that is this blue line right here. And this is actually an HE 561. That's a variable geometry turbo that's on the ISX Cummonses. Good luck getting a hold of them, or good luck getting a hold of them and then coming up with a way to control it. Let's go to Garrett. Garrett sometimes gets over. Oh wait, before we go to Garrett, let's stop in here at the S510. 80, 90 pounds, so 85 pounds a minute. There we go, up to the 6-to-1, way in the surge, so that ain't gonna work. Let's go to a, oh man, everyone likes the GT55. That's a bad dude. So let's go to GT55. Let's get around that 85. Let's take it up to 6-to-1, because actually a GT55 will almost operate at 6-to-1 on the map. So we go there, up. Nah. We're in the surge. Not usable. GT47. Now granted, they've been upgraded. There's Series 2. There's a lot of upgrades to these turbos, but they're not going to make that much different. If you're out here, the latest and greatest is not going to put you on the map. GT47, back to the mid-80s. Up you go. Upwards to 5-to-1. And more than likely, this line is going to continue this way. So 6-to-1 is going to put you over speed and in surge. So that's not going to work either. All right, let's look at this turbo here. We're just going to go right to it. No, we'll do one more. GT4508. That's a pretty popular turbo. Mid-80s, up you go. 4.5-to-1, 5-to-1, 6-to-1. More than likely, you're in surge and overspeed. But here's what I want to see. This is pretty interesting. I don't know why, but this turbo, maybe it's old school. It doesn't, in my opinion, this turbo does not get the recognition it deserves. This is the 4202. I mean, this is a very common turbo. Mid-80s, on up. And what's interesting about a 4202 is, oh, you know what? It doesn't go to 6-to-1. I thought it went to 6-to-1. Anyway, so 4202, up the mid-80s line here. There's 5-to-1. which most of these don't even have a 5-to-1 map on them, and then going up to 6-to-1, a 4202 is almost capable of delivering what you need, other than the efficiency is going to be terrible and the overspeed is going to be terrible. But the surge line is pretty steep on a 4202. So believe it or not, that's kind of an unsung turbo. And what's interesting is that is the go-to turbo for the tractor pulling classes that have a 3x3 rule: 3-inch inlet, 3-inch outlet. 3-inch inlet on your compressor, 3/8 outlet on the turbine. Now, obviously, they modify them, but it is a pretty capable turbo. Now, the most practical way to get 800 horsepower out of 3,000 RPMs is going to be with compounds, and I'm not gonna get into compound sizing with this video, but what happens with compounds is to achieve that 800 horsepower, you've got to have that 860, 870 pounds or 87 pounds a minute. You got to have it. There's no exceptions to it. What compounding does is allows you to take this S500, put out 85 pounds a minute. Guess what? It's in the 78% island because you're only running at a 2.2 to 1 pressure ratio. You're talking 25 pounds roughly. That's why compounding is so good, because it allows you to run this thing at 78% instead of trying to jack it way up here to where it's making hot air, basically. Let me go back to the Borg Warner. I don't have the Borg. Actually, I do have it. Right here I do. Let's go back to this. So that's why, like, this new 488 is a bad dude here. Where's, well, we don't even need to go to 488. Here's 482. 85 pounds a minute. Take it up to, let's see, this island here is 75% efficient island. Take it over to 2.6 to 1, and then you feed that into a smaller turbo to jack that up to get your 6 to 1 that you need. See, that's why compounds are so good. You're starting out with a big turbo, and you're not asking a whole lot of it, and you're asking a lot less out of your little turbo on the manifold too. Here we go. Here's that 488. That's fairly new. 85, between 85 and 90. Take that up to 2.6 to 1 ratio. 26, 27 pounds of boost is all that is. And that's sweet. You got it right there in the sweet spot. So I think that pretty much covers the things that I'd left out of the other video. I'm going to guess that maybe in the next video we'll go into maybe we'll go into compound, really go to A to Z in compound sizing. Or the other thing I might do is I might jump up to 4,000 or 5,000 RPMs on this 5.9 and show you the difference and how much easier it is to achieve more horsepower with 1,000 more RPM, because the big challenge is not 800 horsepower. The challenge is doing it at 3,000 RPMs. And the other thing that does is, look at the torque. To get 800 horsepower, 798 at only 3,000, you have to have almost 1,400 pounds of torque. That's hard on everything. It's hard on clutches, hard on transmissions, hard on rears. It's killer. If you take this number, keep it the same, but raise that RPM up to 4,000, these numbers go way down, because torque and horsepower are nothing but math. But anyway, that's enough for this video. That's probably what we'll cover next time, is doing everything at 4,000, and we might try 5,000 just for like a sled pulling type application. But anyway, that's it for this time. Buster out.